And today we again going to do a bit of that before we move to the main content. So today, first we'll do some refreshers on some essential contents because this is we will be requiring a lot. So just reminding ourselves, and then we'll be looking at rare earth magnet materials property and what's happening in that area. After that, we will again go back to basics, looking at the synchronous machines. And when we do synchronous machine, I will try to show you what's different in a permanent magnet synchronous machine compared to a conventional machine. And then we'll introduce you to the permanent magnet machines so that we are ready to do real finite element type design or design type of discussion after we come back on 26th December. So on 26th December, actually, we'll be looking more on the finite element. So I did not want to start that today because we may not be able to finish. So we'll try to do today just kind of introduction to do that. Okay. So yesterday we talked about a few things. One was the reluctance. Okay, how do you calculate reluctance in a magnetic circuits? One thing we need to remember is that for calculating reluctance, we must know permeability of the material. And if we have saturation, then permeability is no longer a constant. So in that case, if we use reluctance or a magnetic equivalent magnetic circuit, it does not give us accurate result. It will underestimate it, flux. And then it also, the leakage and fringing is always present in electric machines because we have a air gap and we do have, that's why we always have leakage and could also be there fringing depending on how is your shape of the pole and tooth, etc. So again, the estimation of leakage flux is quite difficult analytically, and that's why we may not, especially in interior type permanent magnet machines, there is leakage, flux leakage, you will see later. So that flux leakage estimation is analytically, like this type of conventional method, is very, very difficult. Okay. The other important thing, which is especially for permanent magnet materials characterization, is the load line. Okay, here you are seeing the load line for a magnetic material. So where this load line comes from, very basic Ampere's law. Okay, so if we have a circuit like electromagnetic circuit like this one, the one that the simple circuit like the one here with a gap, air gap, a steel ring, and let's say a coil, something like this. Even for this type of circuit, if there is saturation, then as we mentioned, we can't use reluctance. We may use this load line method. Okay, so load line method, you need to know what is your property, BH property of the material, and then we can use the Ampere's law and write it in such a way that it gives us a equation of a straight line. Okay, so in that straight line, if we plot over the BH characteristics, we can find a coinciding point, and this point becomes our working point. Okay, so if there is saturation, if we don't know permeability, load line method could be an alternative to magnetic circuit, uh, equivalent magnetic circuit method of calculation of reluctance. Okay, but again, this load line method for your magnetic, like devices such as permanent magnet motors, we must know this BH characteristic very accurately. Okay, only then this method can give us where is our operating point, and it gives only for one single operating point. Okay, but in a motor you could have many different operating points. So again, it's not this conventional traditional methods are not ideal. Okay, but they could be useful to see where will be the main operating point, let's say, of the machine. And we must know the geometry. So some limitation, we must know the BH characteristic, we must know the geometry of the motor very well to do this type of method, to use this type of method. Okay, the load line concept is also can be used with the magnets, permanent magnets, to see where it will operate when it is in a motor or in a magnetic device. So for that, so we discussed this yesterday, but like today we'll be trying to see a few more things. So we learn how to, or we recall how to do the reluctance calculation for steel material. And this one we will try to look at how to represent the magnet as a with reluctance as a flux source. Why we can represent a magnet like a with a reluctance and a flux source if we want to use equivalent magnetic circuit to do some initial calculation. Okay, so for that we may need the concept of load line, what we were talking about. So today this section we will be trying to see how to represent permanent magnet in an equivalent circuit. Then we will be try to look at the properties of the rare earth magnet materials, and later we'll be looking at a few like concepts, just recalling how do you calculate inductance, what's the relation of iron loss and iron or core loss with that flux and frequency, etc. So basic concept. Okay. Now let's look at the permanent magnet materials. The difference between a permanent magnet material and steel material is, if we look at its hysteresis loop, you will see the permanent magnet material hysteresis loop is very fat, very wide. Okay, here is your steel material, here is your permanent magnet material. And the region probably all of you know, because the magnets is very difficult to demagnetize, right? So demagnetization happens in this quadrant of BH characteristic. If you apply a negative H field, your B starts to reduce, right? From our hysteresis loop concept, we know that if we apply positive H, flux will increase, flux density will increase in an electromagnet. Similarly, in a permanent magnet as well, if we apply positive H, flux B will increase. So when the magnets are constructed, initially they do not magnetize it nowadays, okay? They will in fact produce the shape that we want, and then everything is ready. After that they magnetize. And how do they magnetize? Actually applying a very large positive H field. Okay, so it will be magnetized to whatever remanence that material is designed for. Okay, and you need a very, very large H. H means current, multiplied by number of turns, Ni basically. So that is how you magnetize. Or once it is magnetized, you will get this remanence flux in the magnet, which is like if you look at the data set of a magnet material, they will give this value, Br, okay, remanence flux density. And based on this value, you will have the various grades of the magnets, especially for rare earth materials such as niobidium, iron, boron. If you look at their data set, or if you try to buy, the grades are determined by what is the value of this Br, and of course also temperature. So we'll discuss the temperature a little bit later. Now if we start applying a negative H, it will start to demagnetize. But it will need a very, very large value of negative H to completely demagnetize. Okay? So once the magnet is magnetized, it is very difficult to demagnetize. That's why we call it permanent magnet, right? It's not easily demagnetized. But when the magnet is in a circuit or is surrounded by steel or iron, it never works at Br, okay? It will operate at a lower point somewhere here, okay, somewhere here. So that operating point, how do we determine this operating point, is again by using actually a load line. Okay, and this load line, in fact, it comes from the same basic concept of Ampere's law. Okay, so we'll look at how can we get that load line in the next few slides, and how this load line can move based on our operating conditions. What the slope of this load line depends on. Okay. And if this load line is very close to, let's say you got a load line somewhere here, then you are at a high risk of demagnetization, okay? So that's why sometimes you may want to check when you first start design process to see where your magnet operating point will be before even you move to your any design, any finite element type of work, okay? So because this point, this demagnetization point is of, or this second quadrant is the most important property that we are interested when we want to use magnet. That's why we don't look at this hysteresis loop or BH loop. We simply concentrate on this second quadrant, and this part can be considered as almost linear. Okay, so when you look at the magnet's property database, you see that they provide BH characteristic is something like this, a straight line. Okay, this straight line is actually come from your BH loops. Okay, so you are linearizing this part, and that's what we see as a property in our data set. And you may, here it was showing for a niobidium material that you may need 1 mega ampere turns per meter negative to demagnetize, okay, very large value. And the remanence is around 1 to 1.04 Tesla, okay, depending on grades. This value is about that. And permeability, relative permeability of the magnets, mu r, is same as, it's actually 1, so permeability is same as air, mu naught, okay, for this is basic property for magnets. And when we look at load line, we'll be actually try to plot against this straight line representing the property of the material. It also depends on temperature. So this 1 megaampere per turn per meter, the negative H, what we are seeing is for a particular temperature. Okay, it could be, it depends, but could be, let's say, about 80 degrees C for a common niobidium iron material. Okay, so if your magnet temperature goes above 80 degree, let's say 120 degree or 100 degree, this point will move to a lower value. Okay, so characteristic will start to look like this. Okay, so this is for a higher temperature, let's say at 100 degrees C. Okay, so that's why when we say that, okay, for magnet motors, the temperature of the magnet is very important. If it operates operates at a higher temperature than recommended, your demagnetization risk increases as well. And so you must monitor sometimes, especially if you know the temperature of the rotor going to be higher, you must monitor that magnet temperature. But magnets are in the rotor, remember, so it's monitoring the rotor temperature is always difficult, even for conventional motors. So monitoring magnet temperature is not so easy. So there are research how to monitor the magnet temperature wirelessly or using some more clever method. Okay, so that's a big research area, how to monitor magnet temperature. That also relates to actually the fault related topic for permanent magnet machines. So when you for more fault monitoring, the magnet temperature monitoring is one of the important aspect. Okay. So here, as I said, how to find that load line. So let's compare what happens to our Ampere's law when we have a magnet and when we have an electromagnet. It's coming from very basic. So in electromagnets, our Ampere's law is equal to Ni, number of turns time current. But when you have a magnet, there is no N, no I, right? So it should be equal to 0. Okay, you could have the core materials Hc. You will have air gap Hg, a flux intensity at air gap, and you have this HmLm is the flux intensity of the magnet. So this Hm is not this, okay? This is Hc or H corrosivity or HCO, okay? This is not Hm. So Hm is we could find by a load line actually. So this operating point gives you what's the value related to this operating point is Hm, and value related the B value related to this point is your Bm, the flux density in the magnet where it is surrounded by iron material like this simple circuit. Okay, so from this equation we can find a straight line equation similar to the one we can find for the steel material. Okay, and if we plot that, you will get your load line for magnet material. You plot that straight line over the BH characteristic of the magnet, and you will know where your operating point is. So this load line, if we look at it depends on the width of the magnet, which is given as Lm, okay, and it also depends on the what is the permeability. So for magnet, usually permeability is constant. It does not change. There's no such concept as saturation. So permeability we can consider as constant. So basically the width of the magnet determines where this load line is. So if you have a very thin magnet, possibly you will have somewhere here, okay, and your demagnetization risk increases, okay. So you can find the where your operating point is. So if you know what is the magnet width you're going to use for your machine, you can calculate out this point by using this simple load line method to see where it will be initially, okay. And you don't want to be closer to this value, closer to this point. Now if we want to use the equivalent circuit, magnet equivalent circuit, again these conventional methods are good to check initially when you when you are starting a design project. You may want to do all this traditional calculation using traditional and this calculation using traditional method to see where you are expecting your operating point to be. So if this type of simple calculation already showing you that your operating point is not where it should be, then you may want to start reconsidering your design as requirements, okay. So for that purpose, the magnetic equivalent circuit or load line method, etc., are good as a starting point. This is like classic textbook method, so anyone can do it. If you know the dimensions, you can calculate it. You will always can find a property of the magnet material from the dataset. So it's all available, okay. And these calculations is a good starting point, okay. Now if we want to use equivalent circuit, we will need to represent the magnet also as a reluctance or flux source, okay. Magnet we can think of it's a flux source. So how do you calculate that? It again comes from, in fact, the same Ampere's law, okay. So this, or rather no, I should say that it comes from actually this straight line representation of magnet, okay. So this is a straight line, right? This magnet BH property of the magnet. So we can represent this straight line quite simply like a straight line equation, right? It will have it has an intercept in the y-axis, so that's your BR. It's like your the intercept of the straight line, and slope of this straight line is your permeability, actually relative permeability. The permeability, not relative permeability. So it's mu m is equal to mu naught, same as air, okay. So that's like your slope time x is your h. So this straight line we can represent by a simple straight line equation as well, okay. And if we just modify a little bit this equation and then multiply both sides by the width of the magnet, we can find that the remanence part of the equation, BR part, if we write it as a flux over cross-sectional area, BR can be written as a flux over cross-sectional area. So that this part is a reluctance. If you recall, reluctance is L over cross-sectional area over permeability. So we have the remanence flux times a reluctance, okay, flux time reluctance, like current time resistance, like a voltage source, right? So magnet can be thought of like a source of flux, a flux time reluctance, okay? And we can represent, that's why it by flux in parallel with a reluctance, or we can represent it as a flux in series with a reluctance, okay? Because we can convert the voltage to source to a current source, so if we consider it to be a current source, we represent it as a flux times as in series with reluctance, or if we represent it as a current source, we present it as a flux in parallel with the reluctance. Okay, so magnet can be represented by its reluctance, which comes from the width of your magnet, cross-sectional area of your magnets, and the permeability of the magnets. Okay, so you can always calculate out this reluctance value, and flux source phi r is simply, you know what is your resonance flux density, and you will know what is the cross-sectional area of your magnet, so you can also calculate this flux phi r. Okay, so magnet can be represented by these two. This is what has been done. You can see back here. So these two example. Okay, this is from two papers actually. These two papers, one is in 2017, other one is in 2020. In these two papers, they try to represent these two motors by equivalent circuit. And the magnet part, here is your magnets. In this case, here is your magnets. In both cases, they are representing it by the flux source and the reluctance. Here as well, flux source in parallel with a reluctance. Okay, so conventional method, everyone knows magnetic equivalent circuit. We can use it to estimate at least initial estimation of flux in permanent magnet motors as well. Okay, so that's the main thing from these few slides. This is a numerical example. I will skip that one because you can look at it later. So I actually made these slides for someone who is not familiar with electrical engineering. So there are some very basic things here as well. Okay, but I know you guys are all doing research and some of you are even faculty, so I'm skipping those very basic ones. Okay. Now we'll move to the magnet material. For all traction motors, they use rare earth material, at least up to now, although there is discussion of using non-rare earth material or using no magnet at all in some designs. Why? We will discuss that as well, okay, in few slides. So up to here, is there any questions? No? If you would like to write down any key points, you can do that as well here. Anyone wants to note down the key points up to here? Yes. Yeah. Yeah. So in this particular circuit, here is your magnet, okay? This part is steel, iron, the white part is iron, and then we also have a air gap. Okay, so we have three different materials, which is same for a motor. you will have magnet, you will have steel, and you will have air gap, okay? But this is a simple geometry, whereas in motor you will have much more complicated geometry, okay? So we just, because we were just trying to develop our concepts, so we use a simpler geometry here, okay? This example actually shows you how this load line is calculated for a particular geometry, for this particular dimension of this simple geometry. And you may note that how the slope of this load line varies. So it depends on the magnet width, as I said, Lm. It depends on the cross section of the magnet. It also, in fact, depends on how big or small your air gap, okay, and air gap's cross-sectional area. Okay, so actually four things. But usually for machine, the air gap length and cross-sectional area is kind of fixed by your stator design or the cylindrical rotor. So SG and LZ kind of becomes constant, and cross-sectional area SM is also fixed by the design. So LM and SM could be considered as a design variable to see where your load line go moving. Okay, if you know this is going to be your width of your magnet and your cross-sectional area, you can see where this point is moving, okay? All right, so let's move then to the next part, the magnet material. Yes. Next one, yep. Yeah. Oh, which one, sorry? Uh, Rotors, yeah, okay. So here, right? So which one are we talking about? This one? This one? Okay, so this is, what is the question? Why is the shape? So this is actually a V-shape magnet, as you can see. It's a V-type magnet, but they are trying to uh, increase the reluctance component of this type of motors, right? You know, for the interior type, this is called interior type permanent magnet motors. So for interior type permanent magnet motors, we have two torque components, okay? The total torque is sum of two torque component. One comes from the magnet and others comes from the magnet saliency or reluctance difference, okay? So if you, in this design, they're trying to improve that reluctance component so that they can use smaller magnet. So you can see they are using quite thin magnets or small magnets, okay? So that means magnet torque will be less, okay? So if magnet torque is less, how do you still get the same amount of total torque? So that means you want to increase the reluctance torque, right? So that's why I believe they are doing all these sort of things, okay? One region, and other region is also like material saving, right? Because usually this back iron, we call it back iron, the iron part below the magnets, okay? This part actually does not contribute much, okay? It just the magnet flux need a path to circulate, right? So if if in the design it is not going so deep, you don't need to have iron material up there, okay? So that's what is another region. And the third region is also for cooling, Okay, so if you have these holes, they are air actually, so you can force air through those holes to cool the magnet. As I said, the temperature of the magnet is a very important point, right? So you want to cool the rotor as much as possible. So sometimes they do force air cooling, or even force liquid cooling. Okay, some liquid could pass through. So there could be several reasons for this type of design. Okay, it could also be these holes, I believe, is to reduce the leakage. Okay, you could have leakage flux. So if you put air there, air gap, the flux, magnet flux loves to go through iron, right? So putting the air there, you are reducing leakage, or making all the magnet flux to go to the air gap to produce your torque. Okay, so many different regions could be. Okay. So yeah, you are seeing a few different designs. We'll look at some of these designs maybe later. Um, but before we can dive into, it's very important for us to understand the magnet material. That's what you will be dealing with. And most commonly used magnet materials are niobidium iron boron, SEMCO, alnico, and ferrite. Okay, so ferrite is the magnet material that you will find in your fridge magnet. Okay, it's the cheapest and easily available everywhere. Okay, but what it is showing here in this column is the density, energy density. So for compared to steel material, niobidium iron material has a uh, very energy dense. Okay, this small amount of magnet can produce equal amount of torque or force as that steel. Okay, so that's what it is. This comparison is. So if we compare between the magnets, actually ferrite, you will need a much larger amount of magnet to produce same amount of torque or force compared to a niobidium iron. Okay, you need much smaller amount if we use niobidium iron boron, and that's why it is everywhere. Okay, especially for high performance traction motor, the niobidium iron boron is T1 what is used. It is also showing you what is where the this is the BR versus H. The BH characteristics operating the points. Okay, so again, if we compare niobidium iron boron, you will get the highest amount of BR, remanence flux, and it will require highest amount of negative H to demagnetize. Whereas in ferrite, it's only 0.5, and it will demagnetize just by 500 kiloampere per meter, a value of H, very small negative field can demagnetize it. So some of you, if you have ever deal with permanent magnet conventional DC motor, you might have seen this kind of demagnetization happening because those motor uses ferrite. Okay, so sometimes DC motors stop working. So why it will stop working? Maybe you'll find that okay, its magnets got demagnetized. Okay, because in DC motor, conventional DC motor, this is uh, especially in the lab, if you use them uh, without much care, because you may not care about the DC motor as much, so these ferrite magnets can get demagnetized and your DC motor is gone. Okay, so it is very easy to demagnetize. However, there is now discussion of using ferrite also in the traction motors, okay, or combining ferrite with niobidium iron, okay, in some designs. So why? because the rare earth magnet materials price and supply issues. Okay. So if we look at the market share of these materials, you will again you will see that it's all niobidium iron for most of the high performance application. Uh, Nearly 60% of the market share is by niobidium iron. Now, what is this niobidium iron consist of? Okay, what are the material it consists of, and why we call it rare earth? Okay, it's not just neodymium; it also have other materials. About 22 to 31% is neodymium. It also have actually some iron, as the name suggests, NdFe, so iron, and boron, so a small amount of boron. So mostly iron and neodymium, okay, composition. And it, in fact, also uses a few other materials, okay, Pr, nickel, cobalt, and Dy, dysprosium. Okay, a few other materials are required to make it a stable magnet. Okay. Now, if we look at why it is called rare earth, we have to recall the periodic table. Okay. So in the periodic table, the heavy materials, if we look at, you will find niobidium is one of that material. The other one that is praseodymium, which is also required in case of as a composite, and dysprosium. Okay, these three components are required to make a niobidium iron boron magnet. Iron and boron is commonly found in everywhere, but these three materials, heavy metals, they are very rare, okay? And we have seen in the previous slide that nearly 30% of niobidium is required, okay? And dysprosium is about 4%. The other one is about 13%, okay, maximum amount. So because of these three rare earth material, these magnets are called rare earth magnet material, okay? And they are rare. You can't find these three materials everywhere in the world, okay? It is concentrated on a few places. One is China, dominated by. I think there's a bit of material also in Australia, but they haven't mined it. Okay, mining. So this is you only 8.5% in Australia, 61% in China, some in US, 15%, some in Myanmar. Probably for India, Myanmar could be the best source, closest. I think India, they haven't found it or they haven't even explored for it. I don't know. So you can see that China dominates here, right? And that's a issue is because of these geopolitical problems. So US only have 15%, right? And if all the motors in your car and all the wind generators and many other motors, brushless DC motors, all if start to using this material, so China is going to be the next Middle East, right? Oil, like the oil, the magnets will become the main thing, right? For a rare earth magnet. So that could be a issue, especially if there is this tension, geopolitical tension. And that's one region, the supply issue. When they say supply issue, this is the supply issue, okay? supply chain issue. The other problem is mining. Why are not like country like Australia, even though they have 8%, they haven't mined it. So why they haven't mined it? Because the mining and producing the magnet is very actually not environmentally friendly, okay, and quite complex. So this is showing you how it can be processed, the material can be processed. As I mentioned earlier, everything is done up to here, and China sometimes sell their magnets without magnetizing. They sell pieces like up to here. They produce up to here, and then allow you to magnetize. Okay, but that process is far more complex than magnetizing the magnets. Okay, you can buy magnetizer, like it's is available. So if you buy non-magnetized piece of magnet using a magnetizer, you can sometimes what they do is actually it's very difficult to handle magnets during construction if you magnetize, okay, because as you know they are very very strong magnet, right, and you are trying to put them in iron, okay, so it's very hard to manage. So what they do sometimes, they put the non-magnetized pieces in the rotor, either glued or insert, whatever, and then they magnetize it using the magnetizer, okay? That's how some of the complex designed magnet motors are produced, okay? But whatever, the rest of the process is far more complex than the magnetization. And because of that, it is not, you cannot, many countries are not processing it or haven't developed the system, okay? Australia is, I think, Australia, the US is now trying to develop the system because of the supply chain issue that I mentioned earlier, okay? We have discussed this a bit. So properties, as I said, this is the linear part of your BH characteristic, which is far more most important. And the BR determines your grade. One more point is the recoil permeability. Sometimes you hear in your dataset when you look at the magnet material or try to buy in the dataset, you may note recoil permeability. So it is the, since it's a BH loop, you may have, like when it operates with AC current, the magnets, like for AC machines, three-phase AC machines, sometimes some minor BH loop can form, okay? So this minor BH loop, when your current is changing. So you could have, especially if we do field-oriented control, you may supply negative ID current, okay? So that means you are applying negative H, like, and you are varying the ID current compared for your operating conditions. So for change of that negative ID, sometimes this type of minor loop can form in the magnet pieces, okay? And so gradient of this minor loop is the recoil permeability. And this recoil permeability, when you turn off the negative ID current, this point can move, okay, and ultimately can affect the overall property, magnet property. So sometimes it is important to note, especially if you know that there's going to be wide flux weakening. That means you will be applying large negative ID current during control of the motor. So in those type of situations, you may also want to know what's the recoil permeability of the material. And this is again, we have already discussed a bit that the load line point, how it moves. Uh, so this you can measure with a parameter how this load line slope moves. And this parameter is known as the coefficient of permeance. What we talked about previously, this is the slope of your load line, okay, depends on the magnet width, magnet's cross-sectional area, air gap's cross-sectional area, and length. So this ratio is defined as a permeance coefficient. So permeance coefficient, if it is decreasing in your design, that means you have higher demagnetization risk, okay, in your design. And if it is going up, it's better, okay. So it is kind of a this parameter is kind of a measure of how your design, what's the demagnetization risk in your design, okay, analytically. And it also a good measure to estimate the location of the operating point, as we mentioned, because it shows you how the slope of your load line move changing, okay. Question up to here? Any question? Okay. Yes, it is always in the second quadrant because once it is magnetized, that this is your property. Okay, this is your property. So it's always here. So if it's a conventional design, okay, there are designs like where you can do the flux, they call it flux modified design. So it's a new type of motor they are proposing where they don't use neobidium iron boron. Okay, some other like material like L-nico can be easily magnetized and demagnetized. So if you use those type of material and you can switch on and off your magnet through control, then only it will could move to the other side, okay. But conventional neobidium iron boron type of design, it always operates in the second quadrant only, okay. So this is the factors, the width of the magnet Lm, okay, cross sectional area of your magnet Sm, air gap length in your design, okay, that's air gap between the stator and rotor, and air gap's cross-sectional area. So these four parameters, geometrical parameter, influences the factor, this permeance factor, okay, which is a quantitative measure of your demagnetization risk, okay. Load line, can it be, it is not possible, right, because you will always have some leakage or you are surrounded, the magnet is always surrounded by steel material, right. So still, if you have steel material, then your Ampere's law will have HClc plus HMLm equal to 0, right? So those two need to be, or even if we consider HC to be 0, that means your steel material is infinitely permeable, then HC is 0, but we have the air gap, right? So even if we ignore steel, we always will have the air gap. So HMLM plus HGLZ must be equal to 0. So H cannot be 0, right? If it is surrounded by. material like other material like steel or air. But if we have only single piece of magnet, then and we do not allow it to leak anywhere, then only you can get BR. So it's never can operate at BR. Okay, its operating point is always less than BR. That's another thing while designing you must remember. Okay. Yes, yeah, that's what you would like. Okay, as if the here you have less um, desmagnetization risk as well as your B value is higher. Higher the B value, it's possible to get higher air gap flux density. Ultimately, air gap flux is what will give you the torque, right? So when you are designing the motor, your main objective is to get the highest torque out of it. Okay, so higher flux density at the air gap is the better. Okay, any other discussion? Okay. This one you are seeing the effect of the temperature and how the demagnetization of the various different material. So we have again, I talked about this before. So if you compare niobidium with ferrite demagnetization, you can know you can easily see why ferrite demagnetizes so easily, right? And the temperature effect. Okay, so this one is shown for 20 degree, the straight line, but if you go to 110, the demagnetization H value of negative H is far smaller than what you will get at 20 degrees centigrade. And there is a concept of Curie temperature for magnet materials. So, including niobidium iron boron, if it goes to a certain temperature, it can fully demagnetize, which cannot be recovered. And that temperature is known as Curie temperature of the magnet material. Okay, it's usually very high, like up to I think for niobidium it's about 200 degrees centigrade. But you never want to operate close to Curie temperature. Okay, you so if a material is graded for let's say 110 degree, you want to operate at 80 degree. You want to always want to have buffer. Okay, so the magnet grade, if you look at the data sheet of a niobidium iron boron, they will have different grades, and the grades mostly based on the temperature. What is their operating temperature, allowed operating temperature? Okay. Yes, here you can see some typical properties of a rare earth material. So yeah, Curie temperature is maximum is 310 to 370 degrees centigrade. So you may think that it's very high. So your magnet will survive 110 degree, but that's not true. Okay, Curie you never want to operate close to Curie temperature. Okay. So you can see that for this particular magnet, Curie temperature 310 to 70 degree, but allowed operating temperature is 80 to 240 degree. Okay. Um, the relative recoil permeability close to 1. That's why you call the mu of the material is same as mu r, mu naught. Okay, because it's close to 1. The mu relative permeability mu r. And saturation field strength, etc., may be sometimes required. Okay, these three properties are not that important, But hardness and the density sometimes is required. Hardness is important if you are going for some high speed applications. So high speed application, you want the magnet to withstand very high mechanical stress, and then you may want to look for what is the hardness of the material. Okay. And another thing, this is actually relates to the supply chain issue that we talk about. Some, like around 2012, 13, there was a price spike in the rare earth materials. Okay. And this price spike was mostly in the dysprosium material, not in the niobidium. Okay, there's some spike also in the niobidium and others, but the highest price spike was shown in dysprosium. Okay, and that led to high price of the magnet material. So they tried to so that there was research to see whether we can eliminate dysprosium completely from a niobidium iron material. Okay, and they developed some magnet with this without dysprosium. So if we do not have this, what does dysprosium do is actually it increases your H corrosivity value, the negative H value. Okay, so lower the dysprosium, it demagnetization risk increases. Okay, there are dy free magnet. You may see some recent papers, they were trying to analyze traction motor with designed with dy free magnet material. And in those papers, they will concentrate mostly on whether there is a demagnetization risk in those designs. Okay, because without dysprosium, the magnets can demagnetize easily. So this graph's just showing you how with the percentage increase of dysprosium, what happens. Okay, so it also affects the temperature. If we don't have any dysprosium, you will get a very high BR value, relatively high BR value for the niobidium, but you will also have very high demagnetization risk for that type of magnet. Okay. So as I mentioned, now there is a big research, especially there if anyone is interested in material science research, there's a big research of developing magnet without using those rare earth material. Okay, magnesium based, iron based. So you can see in this slide, this graph, different type of materials being developed all over the world. Okay, which can replace niobidium iron boron. Okay, but most of them, if we compare their BH energy density and their performance in temperature, you can see none of them yet to be able to compete with niobidium. So niobidium is here, rest is there. Okay, but they may be better than ferrite at least. Okay, and so there is the most recent design people are trying to do is using this type of material and trying to see what changes the designs will require if we go for this type of magnet materials instead of niobidium iron. Okay, and those designs are known as rare earth free design. Okay, not using rare earth at all, but they still use magnet, but rare earth free magnet. Yes, so I think we could take a break perhaps at this point, right? And please think about the key points. And after that, we'll move to the synchronous machine basics, but showing you the difference in those conventional synchronous machine, what is different in a permanent magnet machine. So textbook things, but what changes is required if it is a PM synchronous machine. Okay? So let's take a break for, I think, 5 minutes, right?